Welcome to Eolian Environments. We're going to be looking at a couple of places, and we're going to start with Zion National Park, which is one of the best kept secrets of the national park system. Here's why. This stuff in the background right here, that is sandstone, and these used to be gigantic sand dunes like in the Sahara today. They were deposited in the early Jurassic, and now they've been exposed due to uplift and fluvial erosion. So let's get started. Okay, we're looking at manganese oxide on this sandstone. That's the black material that I'm zooming in on. This is actually a form of chemical weathering that can expedite the process of mass wasting, which is a very common problem in this park. I'm going to do a panoramic view and talk a little bit about this slide. Slides are planar. You can see that planar surface, flat surface, and where a whole section of rock just let go. So the question is, why did the top not let go? It's a little bit stronger. That's called better differential weathering capacity. It has a lower differential weathering capacity than the stuff that slid off. And then you might wonder why this stuff is white in the background, even though it's the same rock. It's a little bit more porous, and groundwater, when this stuff is buried, allowed that groundwater to penetrate pretty well through that rock, kind of washing out the iron.
Boy, that really...
All right, so the sandstone is all Navajo, early Jurassic, and you have to imagine that these were giant sand dunes. And now they're hardened. That means they're lithified in geologic terms. And you might wonder, why is part white of it, one color, the other color is red? That's to do with porosity. The more porous the sandstone of how it was deposited, the easier it is for the groundwater to penetrate through it, so it kind of bleaches it out. So the top part had a little bigger distance between the sand grains, where the bottom section right here, where it's all red, did not. So you're looking at about 15 million years worth of sand deposition to create this. I'm at the eastern side of Zion National Park. This is my personal favorite side in terms of cross bedding, and you can see why. I'm going to be zooming in on some of this for a minute. And I really want you to look at the angle of these beds. And I want you to imagine that these were ancient sand dunes back in the early Jurassic period. Now these sand dunes are stacked one on top of the other, and they've been hardened and lithified into these remarkable stories that show a series of millions of years of deposition of massive sand grains. One thing to consider is there had to have been a source of sand in order to create the materials to make this remarkable place known as Zion. That means there was a source of quartz-based sand which came from mountains, specifically the ancestral Rockies. So you can see the angle of deposition, which is usually around 31, 32 degrees in Eolian environments. So in Zion, there's a famous place called Checkerboard Mesa, which you're looking at right here, and it gets its name from the checkerboard pattern from jointing that has occurred in the rock formation of the Navajo sandstone. The way the jointing gets there is, this is in the desert, Eolian environment, and it's high enough in elevation that this particular area can get quite a bit of frost wedging. So when it does, it actually splits apart the rock and creates this unique pattern. You can see this many places throughout the park and outside the park where the Navajo formation exists. So you can clearly see those jointed lines, and that is definitely caused by mechanical weathering known as frost wedging. This is Lake Mead, and this is what feeds the water to Las Vegas and surrounding regions. It's dropped substantially in the last few decades, and you can see the white bathtub ring. That'll look familiar to you a little bit later when we look at another lake that's been dammed up along the Colorado. This is kind of a sad story, so stay tuned for more about Lake Mead. Welcome to Saguaro National Park near Tucson, Arizona. And one of the things that makes this particular national park so special is the fact that it's in the Sonoran Desert, actually the northern section of the Sonoran Desert, which covers parts of Arizona, Mexico, southern part of California. It's very unique in the fact that it is a very hot desert, and it gets its rainfall in 2 major bursts a year. The bursts allow for the symbiotic relationship of these remarkable cactus that you see here, other desert fauna and flora that can live both in the cactus and around the area. One thing that's interesting about this desert is it's really no more than about 10,000 years old. So geologically speaking, this is very young. A climate shift that has allowed these remarkable cactus to grow. By the way, it is illegal to harm, to shoot, to wound, to kill, to do anything with these cacti. It's protected by law. The matter of fact, another thing I might point out is the older the cacti, the more arms it has, the longer it's been growing for hundreds of years in some cases. Some of these cacti actually have flowers. They provide an important food resource and habitat. I'll also point out some of these have holes in the cacti which serve as a place for birds to take refuge and other wildlife in the area. While we're here, I'd like to address some of what you're seeing in these. While these may just look like trail paths, there's also dry washes, something to be very concerned with in the desert, because dry washes, when it does rain, will flood. And the reason being, as we kind of shift back this way, I'm going to zoom in on the ground cover. The ground cover is very dense with what looks to be just rocky material called desert pavement. That prevents really good infiltration from occurring, and that's one of the reasons these cacti have developed as we look around, and it's so thick in this particular region of the Sonoran Desert. As an FYI, there are 2 sides to this park, an eastern and a western. The eastern is a good hour away from Tucson, and then the western is pretty close. And that's where we're in right now, is at the visitor center of the western entrance of Saguaro National Park. Welcome to Antelope Canyon. Antelope Canyon is located outside of Page, Arizona on Navajo Nation's land, and it is a slot canyon created by flash flooding. We're here looking at the Jurassic-aged Navajo sandstone, and we're going to be walking into a slot canyon to show you how they form. So get tuned. You're going to see some really cool stuff as I zoom in right here. Take a look at this narrow opening. That is actually the canyon opening. The canyon is very young in comparison to the age of the rocks, which is a cross-cutting relationship. While we're here, I'll also point out you can see some really good cross-bedding, and where you see the cross-beds kind of go horizontal and flat, those are truncated dunes, meaning something came up and slopped off the top of that sand when it was being made, and then new layers got put on top. We can look at sand dunes and kind of determine speed of wind and deposition by the angle of the beds. As we are walking through Antelope Canyon, you're going to notice how red the sandstone is, and that's because we have tightly compacted quartz-based sandstones which have made up the Navajo Formation. I might point out that that's the same formation that you saw in Checkerboard Mesa and Zion National Park and so forth. As we're walking through this, you can actually see where the water has swirled through the canyon, creating a slot canyon, and we're walking through the lower canyon of Antelope Canyon. It's a wonderful, beautiful place to visit, but with it comes some remarkable evidence that the danger of flash flooding is real in this area. A group of people lost their lives a few years ago when flash flooding caught them in this canyon. Greetings from Lake Powell, specifically Glen Canyon Dam. This is one of 2 major hydropower dams that exist on the Colorado River. And I want to give you a little bit of background on them and how they came to be. In 1922, a river pact was made for the first time dealing with 7 states that use water from the upper and the lower basin of Colorado River respectively. The upper basin has states like Wyoming, Utah, Colorado, and a handful of others. And then the southern basin, or the south basin, bottom basin, is the one that has Arizona, Colorado, and Nevada. So the lower basin and the upper basin get the same equivalent amount of water usage a year out of the Colorado. They each get 7.5 million acre feet. So an acre foot is an acre of water filled with a foot of water. So it's an acre of land filled with a foot of water. So in acre feet, that number that they allocated based on the initial pact that was made was really based on inadequate years. They used heavy rainfall years, it turns out, instead of an average between drought and heavy rainfall years, making the data not so usable once population grew. And that's where we are now with the water situation that we have. So as you look at this, I want you to see the white bathtub ring and notice that that's from a drop in Lake Powell. That's where we are. And this feature right here is kind of important. That's a security measure to keep boats from coming all the way up to this dam right here. Dams really started getting protected in a unique way starting in 9/11. Same thing with water supplies in order to protect these reservoirs from terrorist attacks. So that's something that's really important to understand. Another thing that was important to the building of this dam was the actual geology itself. The geology that you see here is the Navajo sandstone, which is early Jurassic in age. It's a very porous sandstone. And the porosity, water travels through it and it oozes out. You can kind of see that in this section right here. That worked for and against the dam because they had to put extra anchor bolts into the rock face in order to keep it from destabilizing as they move forward. Now you have to imagine the mighty Colorado used to be a lot more mighty. They called it the Grand River, but it got renamed after the water pact to the Colorado River. And the mighty Colorado River changed once we put these dams like Lake Mead and or what you would know as Hoover Dam and then Glen Canyon Dam as we are here right now. So we're going to look at one of the famous places that's in Las Vegas, which is the Bellagio Hotel and Casino. But one of the reasons I wanted to show you this was to kind of link it back to Lake Mead and to damming up the Colorado River, known as the Grand River. And then yet you see this kind of activity in Las Vegas. I wanted to point out before it's easy to judge these hotels that they're actually implementing excellent water conservation measures. They have to. It's required in the desert for drought contingency planning, and they recycle all of their water. So this is a really interesting thing if you've not seen it, and it goes off like every hour, and you can go observe it to music. And it changes songs every hour, and it changes its dance. But I wanted to point out that there's all kinds of conservation measures in the desert to deal with water, because water quantity is a great issue, not as much as water quality is in the desert. So when you're thinking about that, and you're kind of putting the pieces together of the water issues in the desert, we saw flash flooding through Antelope Canyon. We saw the dryness, but yet frost wedging capabilities of Zion. Now you're seeing Lake Mead and Lake Powell, ultimately, which Lake Mead feeds this water right here through the hydropower dam of Hoover Dam. You kind of can link the pieces together that the desert is a complex system and water is an important part of that complex system. So I'm going to let you enjoy the show, and more to come. I'll finish it up when we return. Welcome to Sedona, Arizona. We are at the Schnebly Hill Formation, specifically on the Bell Rock member. And the Schnebly is divided into two formations. The reason that's important is they represented different depositional environments. I wanted to focus in on some of the features you're seeing in the background that I'm zooming in on. These are some spires, an occasional hoodoo, and a series of buttes. Well, the difference between a butte and a mesa is a butte has a bumpy top, and mesas have flat tops. There are very few mesas out in Sedona, but a lot of buttes, including the one that we're sitting on right now called Cathedral Rock. So all of this was deposited during the Permian period. The Permian was the end of the Paleozoic and represented a drying up of the North American continent and worldwide climate because of the formation of Pangea. Unusually, we had a transgressive sea, the Petagosa Sea, came in this way and deposited an unusual formation called the Fort Apache Limestone, which I'm going to zoom in on and notice the blocky texture, I think. Yes, there it is, the Fort Apache Limestone. And so this is an anomaly in these sandstones, and interestingly enough, the sandstones are inland sand dunes. These should be cross-bedded, but they're not. And the reason they're not is because they got reworked by the coastal waters that came in as the transgressive sea came into Arizona out of the Colorado area. Welcome to Bryce Canyon National Park, home to the world's largest concentration of hoodoos. Hoodoos require several things in order to be made. They require, number one, a cap rock. Something hard that can anchor in the sediment so they don't erode very fast. And I'm going to zoom in on some of these and show you the tops of them. You can see a pretty tough rock there. Well, that's the cap rock. These sediments that are underneath it are a little bit softer. When you get a really fat hoodoo, that means that the sediments that are there, like these over here, are a little bit tougher than the stuff that's really skinny. But again, the cap rock's still harder that's on top. The second requirement that you must have to make a hoodoo is really important. High elevation that would produce frost wedging most of the nights of the year. So we just left Zion Canyon this morning, and that national park does not contain hoodoos. Several reasons why it can't, because the rocks are different. These rocks are very soft. We're looking at the Claron formation that was deposited at the beginning of the Cenozoic era, specifically in the Paleocene epoch. Paleocene lasted 10 million years and represented a time of recovery after the mass extinction event of the Cretaceous period. So fascinating that the first set of rocks, if you look at the bottom, and I'll kind of zoom in on them, they're called the pink member, and the pink member would have represented siltstones and some sandstones and some limey muds that would have come down river basins at the time of the Paleocene. We had a mountain building event that occurred at the end of the Cretaceous on through the Paleocene, Eocene, and parts of the Oligocene called the Laramide orogeny, which would have produced mountains in this area. So interestingly enough, those mountains would have created the rivers that made the pink members that you're seeing here. More noticeable probably are the white tops to all of these things. That's the white member, and the white member represents lacustrine or lake deposits. You have to imagine, let me kind of do a scan of the area, that this Pongzanote Plateau would have been a big giant Great Lake region. And that Great Lake region would have deposited lots and lots of siltstones and clay, like shales, that make up the white member. That's why the white members typically are skinnier than the pink member, because they're softer. So in conclusion, Bryce Canyon has the remarkable things that make up the requirements to make the world's highest concentrations of hoodoos around the world. Interestingly enough, the plateau is eroding at 0.3 meters every 100 years. If that doesn't sound like much, a foot every 100 years, well, it is over 1,000 years, 10,000 years, a million years. So in a million years, we would have retreated this rim that we're sitting on right now, and I'm kind of giving you a look at that, by 1.9 miles. So eventually these hoodoos will turn into spires. Let me kind of zoom in on one of those. These spires here don't have a cap rock, or you can see they're missing that. They're going to topple over and new hoodoos will replace them. So let's quickly talk about how a hoodoo is formed. Hoodoos start off where there's jointing in some type of a fin, F-I-N, and the fin is created by a joint in the rock formation itself. And the frost wedging, when it gets really cold at night, will allow those fins to break open about 7 times the size that the joint was if you do it repetitiously day in and day out. So really about 200 or more days a year reach the frost wedging capacity here at Bryce Canyon, because we're sitting over 8,000 feet right where I'm standing right here, and it gets over 9,000 feet on at the top of the basin.